It's going.
After we get everybody in, we'll just get started. We had a couple warm-ups this week, right?
I think we had one or
Like,
two.
yeah.
Yeah, so for those two warm-ups that we had at the top of the week, just go ahead and upload those to classwork week 2 on Google Classroom whenever you get the chance. I'll be putting a grade up for those today.
Okay.
Here's all we're going to do today. Today I'm going to go through the process that I expect y'all to go through in order to analyze the data. And like I said, we're analyzing the data in 2 ways. The first way is easy, and the second way is far more subtle, far more technologically demanding, which is why we're going to go over that today. So the first way in which I expect y'all to do the data analysis for this lab is, number 1, we want to get a period for each of these systems that is theoretical. And so this is going to be according to the equations. And I want you to take that and compare it to the period actual, which we get by reading it from the data. So looking at those graphs on the Excel sheet and reading the period off of it, which is the amount of time needed for there to be one full oscillation, which is to say the time that it takes to do an up and a down. So the amount of time to do that would give us a period, or the amount of time to do any full cycle. So here's a look at what another way that we could time out a full cycle from top to top. And these two are equivalent simply because a full cycle has 1 up and 1 down. And notice here, this is also a full cycle because it is 1/2 of an up, 1/2 of an up. 1/2 plus 1/2 is equal to 1 full up and 1 full down. As long as you have 1 full up and 1 full down, it constitutes a full cycle, even if the way in which it does that is ugly.
Mr. Robinson?
Yes?
I'm sorry, but for the classwork, did you want us to include last week as well, or just this week?
There was a separate place to upload last week's classwork, so if you didn't do that, please upload that to classwork week 1.
Okay, thank you.
Yep.
Mr.
And then
Robinson,
yes?
is the theoretical period, I mean the actual period, the list in seconds on the Excel sheet?
It's not just the list in seconds. The seconds is literally time counting forward in even intervals. In order to read the period off of that, you're going to have to read the graph. So here is the Lab 8 data for the second spring mass oscillator, which I'm going to be doing my tutorial for the data analysis with today. Like I said, 1 full period is from an up to an up. So if I put my cursor right here, right, that's going to give me a combination of values. So that's saying that when time is equal to 1.92, the amplitude is 6.78. And then at my next up, the time is 2.26, and the amplitude is 6.6, right?
Yeah.
And so this time, 2.26 minus this time, 1.92, that time difference should give you back the actual period. And it should be the same spacing between any of these peaks. So literally just go to the data sheet and then take the time difference from one peak to another.
Okay.
Is that okay?
Yeah. Thank you.
Okay. Yep. And yeah, so that's what you'll be doing for the determination of period. Are there any questions for the first part of the data analysis? No? Okay. And here's the second part that we'll be talking about today, and this is going to be a bigger discussion of skills. For the second part of the data analysis, what I need you to do is I need you to experimentally determine a damping constant. So determine the damping constant by means of regression, which we'll talk about what that is today in the form of a tiny lecture. And then I will show you how to determine that damping constant by regression. And this we can't verify with a % error the way that we can here, because your answer won't just be a single number. What I'm going to ask you to do once you determine that damping constant by regression is to then graph your motion in Desmos. and then compare and contrast it to the actual data in Excel on the domain of x is equal to 0 until x is equal to 15. And why would we analyze it on this domain?
Because we use time 0 to 15 seconds.
Correct, because when I did the lab for y'all yesterday in the space behind me, yeah, all of those data sets ran from 0 seconds to 15 seconds. So you want to try and produce basically the exact same graph, but instead of producing it point by point, you should be able to produce it with functions. So let me show y'all a tutorial of how this is done. And then we're going to talk about COVID-19.
Let's do it.
Okay, so number one, let's talk a little bit about what regression is as a mathematical theory and as an object. So this is the Wikipedia page for linear regression. And what linear regression is if you have a set of data which is roughly linear, like it is in the default picture for this article, there is a mathematical technique which will produce for us a line that tries to latch onto what this trend is. Whenever we actually analyze mathematical data in science, there's always a little bit of messiness and a little bit of noise. And actually data that doesn't have this feature is typically thought of as counterfeit almost right away. That nature doesn't produce perfect data. There's always a little bit of statistical noise. And the way that you determine this regression line isn't just by taking a pen and drawing a line through the middle of the data. There is actually a series of steps that one would take in order to figure out what is the best fitting line to the data set. And the procedure that you would do in order to get this scales non-linearly with the number of data points in the set. So if you're doing this for one data point, it doesn't make sense, can't do that. If you're doing it for 2 data points, then you're just doing a regular old, use those 2 points to solve for the slope, use those 2 points to solve for the intercept. So if you have 2 points, it's 2 calculations. But the more and more and more points you introduce, you have to do 1 calculation for every relationship between those 2 points. So 2 points is 1 calculation, 3 points is 3 calculations, 4 points starts to get you to 4 times 3 times 2 times 1. So that would be 12 calculations. And the more points in your data set, the more non-linearly it's going to scale. When mathematicians invented this approach, we figured that it would just be impossible to do this for an extremely large data set. But that's because the people who were working on this technique of regression were working on this in the 1800s and 1900s. And then of course came, the invention of computers, which then made it possible to quickly do this long set of calculations necessary in order to produce an equation of best fit. Moreover, now that we have access to more powerful computing hardware than we did before, not only can we do linear regression, we can do all sorts of non-linear regression in order to produce various trends. And let me just remind you real quick what it is that we are doing. We are trying to take this trend right here where I have y is equal to e to the negative kx. That's our damping constant term, right? So k is the number that we are trying to find out using Excel. And then on the inside here, I just have the oscillatory term. And what we want to know is, well, how much damping is there really in our system so that it flattens out at the correct rate over time. We want to try and separate what the damping part is doing, separate and apart from what the oscillatory part is doing. Is that okay?
Yep.
Are there any questions there of what the generalized goal is? No? Okay. So let me show y'all the technique in terms of what it is exactly that I'm asking you to do in this lab. So I'm going to do this example for the spring mass number 2 Excel sheet, just because this is a beautiful graph right here, the force graph. This is textbook oscillatory motion with damping as we go off to the right. And so what I'm asking y'all to do, and let me make this half the screen. And then I'm going to open a new Excel sheet to the right, and I'm going to share my whole window. Give me 1 second here. Share. Give me a blank spreadsheet. Okay, so y'all can see my whole window, yeah?
Yeah.
Okay, so what I'm gonna do to try and figure out, how much damping is there here? How much is there really, right? Is I'm going to take and I am going to pull only the peaks. Now, the reason why is that the exponential decay part is what is connecting these peaks from one to the other, 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 as we go to the right, and the values get smaller and smaller and smaller and smaller and smaller, right? And so to remove the oscillatory motion, what I'm going to do is I'm going to ignore the fact that we're oscillating up and down, and I'm only going to take the maximum amplitudes at the top of each one of these so that I can see how that maximum amplitude is changing over each cycle. So I'm going to pull this first data point, and I believe that data point is 1.92, comma, 6.78. So in my new sheet, I'm going to have the time, and I'm going to have the amplitude. Please follow along at home if you will. And this time right here, like I said, is 1.92 seconds. And the time, and the peak is 6.78. And now I'm going to do that for the peaks as I go across the table here. So 2.26, 6.60.
Are you gonna do it for all of them?
Yes.
Okay.
And I mean, maybe not all of them. You should do as many of them as you can get. The more data points you get, the more robust your data.
Okay.
And again, if this were an actual experiment that I was doing, I would write a script in Python that does this part automatically. That automatically goes for each amplitude, pulls out the maximum value, and then also reads me off what the amplitude is at that point. Because if you're doing this for hundreds of thousands of data points, you would definitely want a piece of software which does it automatically. This is high school and you're all stuck at home, you have time. So I'll just expect y'all to do this by hand. Or maybe, split the work up with your group mates and have each person do one sheet and then compare when you're done. So that one goes with 6.36. I'll only pull 2 more, but like I said, take as many of these data points that the graph will allow you to read off. So 3.86, 6.4. 3.88, 6.36. A couple more. 4.2, 6.33. 4.52. 6.30. All right, is this first part okay?
Yes.
Okay, so all I've done was I pulled the times and the amplitudes. So here's what we're going to do in order to figure out how much damping there is. I'm gonna take these 2 rows and I'm gonna select them, and I'm going to insert a chart. And it's just going to give me a breakdown of the values here, right? And so for my chart type, I am going to choose Scatterplot. And then I am going to, man, I'm a lot more comfortable with Excel than I am in Google Spreadsheets. Let me switch to Excel real quick. Though it's exactly the same, just the menus are laid out in a way that I already know.
What's
So
What's the real difference between Excel and Sheets?
To be honest with you, nothing in terms of what they can do. Google Docs are nicer because you can share them with other people and look at what's happening on the page, get updated in real time. You can't do that in Excel. I like Excel because I've been using Excel since like middle school. And so I have all of the functions in it memorized. It does all the same stuff. It's just that, like, because I'm so used to Excel, the slight difference in the positions of stuff in Google spreadsheets messes my brain up.
At what level in mathematics would Google Sheets be useless?
Google Sheet, I mean, if you were doing like astronomical work for NASA and you were trying to process a data set of 1 million points and do a bunch of different functions on it, it couldn't do that simply because it would run out of memory. But in terms of like anything reasonable that you would end up doing for a job, unless you're a scientist, Excel can do it all. Let me show you what I mean by that. So like I said, I just took the data points off of these maximum amplitudes. I pulled them off of the sheet and I fed these into Excel. So what I'm going to do now is in Excel, I'm going to insert my scatter plot. So here are the points, right? And it's a little bit noisy. It's always going to be that way. And now I'm going to click the data points themselves and I'm going to right click them. And I have a couple different options here. And the one that I'm looking for is add trend line. So I'm going to add the trend line here. And it's going to give me a lot of choices in terms of like what kind of trend line it is that I'm going to insert. Let me go full screen with this one now. And so here's my trend line. And check out these options. I have exponential, logarithmic, polynomial, power, and moving average. So if I choose polynomial, this is going to try and fit it with a quadratic. If I choose logarithmic, it's going to try and fit it with a logarithm. If it's linear, it's going to try and fit it with a line of the form y equals mx plus b. And which one you choose, what do you think that depends on?
Is it the decaying
So we're trying to figure out the decaying constant, and because I do physics, what kind of equation did I say that should be?
e to the power of negative kx.
It should be exponential, but what I'm asking is a more general question. What I'm asking is, how do you know which equation to choose? What kind of trend line based on your graph? Well, the only thing you can do is use your intuition, know what shapes these equations are, and use the correct one in order to model it. I'll talk about that more when we look at some COVID-19 data, yeah? But like I said, I'm just telling you as a fact, as a physicist from one to another, damping typically plays out exponentially. And so for my trend line, I'm going to choose exponential. And it's going to draw it in here. This is a little snippet of an exponential decay graph over this region, the one that matches best. But what I'm going to do is I'm going to click this button here to have it display the equation on the chart. Check this out. Can y'all read that?
Mm-hmm.
Yeah.
Let me make it bigger. Or easier, I'll just zoom in. And once you have it do the exponential regression, right, it's going through some really long, complicated process to get this equation of the line. But what it can tell us in the end, if we have it display the equation on the chart, is it'll tell us that damping constant. And in this case, for this graph, the damping constant is negative 0.027. So with that K in mind, I can now go back, negative 0.027. I can go back and I can build out my entire model for how this function behaves. So this constant was for spring mass set number 2. So let's go ahead and use the basic information for spring mass set number 2 in order to predict what the period should have been, right? So how do we do that? What's the equation?
Is it t equals 2 pi over
T is equal, so this will give us the period. T is equal to 2 pi root what?
k over m.
K over m. And for spring mass set number 2, we're going to need both of these numbers. The m is easy. For that one, m was equal to what? It was on that Excel sheet. It's on the first page where it says basic info.
Oh.
So here's what we know about the spring mass oscillator set number 2. We just got its K constant for its damping by using regression. The mass is equal to 0.058. And the other thing that we're going to need in order to build out this guy's model is we're going to need that spring constant K, right? And that's why I gave y'all the displacement. Yes?
I think it's m over k. We did k over m last time.
Yeah.
Oh yeah.
Yeah, I said that last time.
M over K. Yeah.
Mm-hmm.
And so we're also going to need to get the K constant, which is why we took down the displacement when I hung the weight on it. So to get the K constant, F is equal to negative KX. F is going to be equal to, I'm sorry, negative F divided by X will be equal to K. And so I can plug in the information that we have in order to get the K constant. The force is just going to be the weight of the weight itself. So that's 0.508 kilograms, then multiplied by gravity, 9.81 meters per second squared. And when we hung it on there, how far did it hang? What was the displacement?
63 centimeters.
Sorry, for mass 2, spring 2?
Oh, mass 2, spring 2.
Yeah, the spring mass systems, what was that displacement?
Oh, it was 2.5 centimeters.
Yep, so we'll have to take that and turn it into meters. So since it hangs down, we're going to say that that displacement is negative. So it's negative 0.025 meters. And so when we take this and we process it, this will tell us what our K constant is for that spring. And in this case, it'll be I believe I'm getting 199 newtons per meter. Oh boy, I don't like that I'm using the letter K twice. Let's say that the spring constant is K. I'll call this other constant D or whatever, just so that we have a separate letter for it. Is this stuff okay?
Mm-hmm.
Okay. So let's go ahead and build this stuff now into Excel to see if, let's build this stuff into Desmos to see if these values latch on to how reality is. You know what I'm saying?
Yep.
Okay, so I'm gonna go back to sharing my screen. And somebody's blowing leaves outside.
Not I.
And so I'm going to head on over here to Desmos. And in this other window, I'm going to pull up the graph from our spring mass oscillator. So here's spring mass number 2. And what we want to do is we want to see if we can make a graph which latches on to the way that this blue graph behaves. So here I'm going to feed in the numbers that we just calculated. What did we say our damping constant was based on Excel?
Oh, negative 0.027.
Okay, so there's our damping constant. And let's see here. This is reaching a peak of 6. The middle number is 5, so this is an amplitude of about 2. So I'll multiply this lead term here by 2. And then on the inside here, what are those variables when it comes to a spring mass? What do we put inside of our cosine to get our equation of motion? It's the square root of what over what?
Oh, is it G over L?
That's for a pendulum. For
Oh.
this one's a spring mass.
Okay.
Again, we got it backwards. On the inside, it's going to be K over
K
M.
over M, yeah.
Wait.
So on the inside here, it'll be 199, that's our K, divided by our M, which is 0.508. And if we look at it here from 0 to 15, yeah?
Yep.
This seems to latch on pretty decently to the way this behaves. This one right here decays even quicker than this. So I would say that this first attempt at getting a K constant, this number might be a little bit too small. If it decays quicker, that means the true K value is a little bit bigger. Let me just fiddle with the numbers. 0.4. Yeah, that causes it to drop off a little bit quicker. 0.6. I assert that the more data points that you pull off of this original trend, the closer that your Desmos graph will be to this motion. But hey man, that's physics. We take some wild, like fancy motion, we hit it with enough math so that we can predict what that motion is going to be on into the future. So the determination of the period part, that's straightforward. The hard part that I'm asking y'all to do at home is the determination of that damping constant. Pull the peak amplitude of each one, feed that to Google Docs, graph it according to a scatter plot, and have it do exponential regression. I'll look up a link of how to do that in spreadsheets for those of y'all who don't have Excel at home. I'll post a link to a tutorial of exactly where those are in the menus in Google Sheets. Cedric, you had a question?
Will this video be up today?
Yes.
Okay. I just joined. Sorry.
And on top of the regular stuff for the lab, when y'all turn this in on Wednesday, not only do I want you to turn in the scans of the lab book and those pages, the other thing I'm going to ask you to do is that once you cook up your models for these 4 data sets, I would also like you to produce for me this Desmos sheet in the same style. And when you're done, title it Lab 8 and then your name. Save it and make sure that you have all 4 built on here, or you could put them on, you know, just build all 4 into the same one. I can just like turn them on and off as I check them. And you will turn this link in along with the rest of the lab report when you submit it. Is that okay?
Yep.
Are there any questions on what it is exactly that I'm asking y'all to do for this lab?
So,
Oh, sorry. Go.
no, it's fine. You got it.
Okay. For the lab data, do you want us to print out just like a tiny portion, like not all of the numbers, obviously? Because
You don't have to get the numbers. The graphs are the important part.
Oh, the graphs. Okay, sure.
Just the graphs of motion, yeah.
Okay.
And did anybody out there install Logger Pro? I'm sorry, Logger Lite from Vernier?
Yeah, I did.
Okay, yeah, so that link is in there. If you just want to pull the graphs out of there and print them straight out of Logger Lite, you can do that too.
Okay.
Any other questions?